Okay, in this lecture video, let's talk a little bit about what the Km really tells us. We now know what it is. It's the concentration of substrate when you're going at half the maximum velocity. But let's think about what does that tell us about the enzyme. So let's consider, again, our little schematic that describes an enzymatically catalyzed reaction. This is the one we keep using for everything. So formation of the complex, and our rate determining step is K2, including formation and product release all in one step. Okay, so we know from derivation of the Michaelis-Menten constant that Km is a function of multiple rate constants. It was K2 plus K minus 1 over K1. So it's a function of these rate constants. But how we really use it is that we use it as an apparent Kd value, an apparent dissociation constant for the enzyme substrate complex. So if we were going to look at that, the enzyme substrate complex dissociating would look like this by itself. If we're just talking about it breaking apart back into the enzyme and the substrate, we know that this would be K minus 1 and this would be K1 in the way that we wrote our original reaction schematic. So we know that if the definition of the Km was K2 plus K minus 1 over K1, under conditions when K2 is really, really small compared to K minus 1, if that's true, then we can consider that negligible, and this becomes K minus 1 over K1, which is in fact the Kd for the dissociation of the enzyme substrate complex. Okay, so under these conditions, Km really does become the Kd. However, we talk about it as a Kd, knowing, though, that it's still a function with this other rate constant included in it. That's why we call it an apparent Kd. But we can use Km then to talk about substrate affinity. So let's look at an example for that. So let's take RNase A as an example. And I've got data, kinetic data, for both the wild type, which is the natural form of the enzyme, and a mutant. So I've got some Vmax data in units of micromoles per minute. And I've got some Km data in units of millimolar, so concentration. So here's my wild type data, and here's my mutant data. So this is 100, this is 1, this is 10, and this is 0.1. And my question to you might be, which has the higher substrate affinity? So which one has the higher substrate affinity? So I would encourage you to pause this lecture video and think about it and come up with your own answer before you hear me explain it. Okay, so pause. Okay, so now I assume you're back and you've thought about this. So I want to think about which enzyme, the wild type or the mutant, has the higher substrate affinity. The first thing I say is it's Km that I want to think about for that, not Vmax. Vmax doesn't have anything to do with substrate affinity right now. So since Km is an apparent Kd, then the greater the Km value, the lower the substrate affinity. So that means it is the mutant that has the higher affinity for substrate because it has the smaller Kd. I could also ask you then, which of these enzymes shifts the equilibrium constant for the reaction that RNase A catalyzes towards product formation? So pause it. So I want to know which enzyme shifts the equilibrium constant for the reaction towards the formation of product. Which enzyme is better at making there be more product at equilibrium than the other? So pause it and think about that. Hopefully discuss it with somebody. So now that you're back, I'm hoping you said neither. Neither. Because we know that enzymes affect kinetic control. It just affects how fast you reach equilibrium. They do absolutely nothing to affect the position of the final equilibrium. So there is no effect on the equilibrium constant for the reaction that RNase A catalyzes.